So let's take a quick look at an example of a use of the comparison test to actually figure out if a series converges or diverges. So the first example we're going to look at is sine n over n squared. So for this one, what we're going to do is we're going to notice that sine of n in absolute value is between 1 and minus 1. So this means that sine n over n squared, that's less than or equal to 1 over n squared for all n. So now that means we can go ahead and use the comparison test. Right, so the comparison test, we're going to compare our series here. We're going to compare it to the series whose terms is 1 over n squared. And now remember, the series n equals 1 to infinity of 1 over n squared converges, right? It's a p-series. And by the comparison test, then that means that the series n equals 1 to infinity of sine n over n squared is going to converge. Well, actually, look at the absolute value bars, is going to converge. Right, that follows by the comparison test and by the observation that we made at the end of the previous video, the series that we started with. Oops. Series from n equals 1 to infinity of sine n over n squared also converges. The next thing we're going to look at is an example where the series diverges, and where we can see that using the comparison test. So here we have our second example. We're going to look at the series k equals 1 to infinity, 2 plus sine k over k. And the key thing we're going to look at here is the behavior of the numerator and the behavior of the denominator. And this is going to be a recurring trick we're going to use in all of these problems. So here the numerator is this 2 plus sine k, and that numerator, this 2 plus sine k numerator, that thing is going to be between 1 and 3. Right? It's trapped between 1 and 3 because sine k is at the smallest is minus 1 and at the largest is plus 1. Okay, and the denominator is looking like k. So this thing is going to be greater than or equal to 1 over k. But we know already that the series 1 over k diverges. So by the comparison test, our series is bigger than something that diverges. That means that our series itself diverges. So that series diverges. This next example is going to be a little bit more delicate in that it won't be immediately obvious what the correct thing to compare with will be. Here we're going to look at the series where we take the sum from n equals 1 to infinity of 2 over the quantity n squared minus n plus 1. Now the interesting feature about this series is that it is not immediately, or it's perhaps not immediately obvious what we should compare it to. So the thing we're going to do is we look at what is the behavior of the numerator and what is the behavior of the denominator. Now the numerator is just 2. There's nothing we can do about that. That's just, it is what it is. The denominator, however, right, the denominator, this is this thing that looks like n squared minus n plus 1. And we look at that and we think, okay, the dominant behavior is going to be n squared. Right? So the n squared dominates as n gets large. Now there are two things we can do at this point. the first one of which we will see in the next video. But so for now, the second thing we can do is to compare this to something. Now, as I said, we have n squared as the dominant behavior of the denominator for n large. So this whole thing is going to look like, right, the whole expression is going to be more or less like 2 over n squared. Now that's a p series for p equals 2, and that converges, right? So the first thing we're going to think is, okay, this series converges because it looks like 2 over n squared. So now what we need to do is we need to really use our tests in order to figure out how to get that. So for this, what we do is we go ahead and we're going to find some inequality that gives us a control over that denominator, right? So an expression gets bigger if the denominator gets smaller. So what we want is we want something that's smaller than that denominator, but that looks like n squared. And so here the trick we can do is we can say that 1/2 n squared is going to be less than or equal to n squared minus n plus 1 for n large. Right? When n gets very, very large, this n squared term is going to dominate on the right, and on the left we only have 1/2 n squared. So that expression is going to be, this inequality is going to hold for large values of n. So then we can compare our series. We can compare our series with the series 2 over 1/2 n squared. And this guy converges, right? That's the series of 4 over n squared. That converges by the p-test. And hence, by comparison, we get that our series here is going to converge, right? Because it's smaller than this series over here that converged by the p-test. Okay, so that's the basic idea here. But the tricky thing, right, as we saw, was that we had to play this kind of a game in order to get the inequality controlling the n squared minus n plus 1 term that we had in our denominator. That's kind of ugly. So what we're going to do is we're going to use a second kind of test that's also a comparison test, but it's something called the limit comparison test.